Isometries, and today we'll speak about groups of isometries. Of Hadamard spaces, and basically we have the Margulis lemma. We want to understand group generated by small elements. So we have epsilon, and we have the thin part of a manifold. With universal cover is the union of d gamma less than epsilon, or less than 2 epsilon, doesn't matter, over all gamma and gamma minus the identity. And so if we are here, we want to understand the elements that are responsible for us to be here. So and the Margulis lemma tell us that the group associated to any point, gamma x epsilon, it's the group generated by all gamma in gamma such that d gamma is less than epsilon, is virtually important. This is the Margulis lemma. There is some constant epsilon for the Margulis constant, and we want to.
The universal cover should be elements.
Sorry.
The universal cover should be lists of things and you wrote things in gamma.
This is how I denote if I have x is the symmetric or the Hadamard space, and gamma is a group of isometries of x, and m is x mod gamma, and if y is a subset of m, I denote by y tilde. It's not the universal cover of y, but it's the pre-image pi inverse of y. So it's the image of in x, the pre-image of x of y. We have the map pi from x to this. Not possible.
No, I get that, but the thing that I'm not understanding is you wrote it as a union of things in gamma, but it should be.
No, this is a sub-level set.
Ah.
D gamma is the distance function. D gamma of the point x is the set of all x such that D gamma of the point x is the distance between x and gamma x, and this is a sub-level set of it. So it's a convex subset of x.
So it's the set of all x. Such.
Yes. And so this group is virtually important. So basically we want to understand such groups. So we want to understand, our target is to understand the group of isometries of small elements in discrete groups. So basically we want to understand groups which are commutative or virtually commutative or virtually important more generally. And we have, remember our picture, which is not so nice in the non-positive curvature. It's nicer in the negative curvature, and this is the same part. So we want something that one thing that we want a direction which increase the inductivity radius. So we want to show that for such a group there is always a direction that increases the inductivity radius. This is one thing that we want. And another thing that we want is to understand the boundary. So we understand all these things are convex sets. So this is d gamma 1 less than epsilon. This is d gamma 2 less than epsilon. But what happened here in the corner? So this is another thing that we want to understand in order to approximate combinatorially the thick part. We want to cover it by balls and make a good cover and look at the nerve and say that the homotopy type of the thick part is controlled, and for this we have to understand the boundary, and to say that the homotopy type of to connect the homotopy type of the thick part and the full manifold, we need this some kind of vector field that allow us to do Morse theory or to apply a deformation retract. So this is some motivation for what we're going to do. So we will start with the commutative group. So let's start with abelian group. I think that at the end of the day, this is the most important case. We can reduce the. In most cases, I know to do it, but not in all cases. To reduce from important to commutative, but we will get to that. So first, lemma. If you have two commuting isometries, alpha beta equals beta alpha, then one thing is that d alpha, this function, this is a function on x, is beta invariant. This is obvious, right? Let's see. D alpha of x, of beta x, is the distance from x from beta x to alpha beta x, but alpha and beta commute, so it's a distance from beta x to beta alpha x, and beta is an isometry, so it's the distance from x to alpha x, which is d alpha of x. So this function is beta invariant. Therefore, the convex set, the sublevel set, d alpha less than any constant a, is beta invariant. Okay? Let me remind you another lemma that we had, in the past, is that if A is a convex closed subset of X, so X is a Hadamard space, is a non-topological space, then there is the nearest point projection, pi A from X to A is the nearest point projection, is a one Lifshitz map, is a contraction, is one Lifshitz retraction from X to A. There is at any point in X, there is a unique point in A which is nearest. And if alpha is an isometry that preserve A, then alpha commute with pi A. Okay, it's almost tautology if you think about it. And then when we apply it to this sublevel set, we get the following thing. So let me call it a theorem because it's extremely important. Suppose alpha and beta are commuting isometry. Then the gradient of d alpha at any point, then for any x, the gradient of d alpha in a product with the gradient of d beta, this is in the tangent space of x, is non-negative. before I prove the lemma, the theorem, let me explain what it means. So I look at the function d alpha, and the gradient, and I look at d alpha less than some constant a. So this is a convex set, and the external normal to it at any point is the gradient of this function. This is the level set. And then I look at the same function, the sublevel set corresponding to beta with another constant, and here I have an x, and at any point the external normal is the gradient of d beta. It's
Even in the boundary or at any point?
what do you mean in boundary? So if I look at a level set, if I have a sub-level set, the external normal is, the level set is the boundary of the sub-level set, and then the external normal is in the direction of the gradient. That's, you know, from infinite. And so this is the direction here. So in particular here, the external normal will be in this direction. The external normal here will be on that direction. This will be the gradient of d alpha. This will be the gradient of d beta. And to say that the angle between them is less than pi over 2, the inner product is positive, implies that the angle between these two boundaries is not too sharp, is at least pi over 2. So a corollary, so I put the lemma, a corollary, the angle between these two sets, d alpha less than a and d beta less than b, the angle between two sub-level sets at any point in the boundary at x is at least pi over 2. For every x belongs to d alpha equals a intersection d beta equals b. That's what it means. And this angle, if you want, is defined as pi minus the angle between the normal. This angle is by definition pi minus the angle between n alpha and beta. So these are the normal. External normal. And they have the same direction of the gradient of the expressive function. Sorry? You have a question? You can ask.
Yeah.
Okay. So let me prove this theorem. Let me prove the theorem. So proof. So the proof is very straightforward. So let x be, suppose that d alpha of x is a and d beta of x is b, and I look at the set A to be d alpha less than or equal to a. It is convex, closed, and beta invariant. So here I use the commutativity. It's beta invariant. Let n alpha and n beta be the external normal to the external normal to d alpha less than a and d beta less than b, So basically, we know that n alpha is the gradient of d alpha if I normalize, and n beta is the gradient of d beta. And so let's look at the picture. So this is d alpha less than n, and I have a point x somewhere here, and I have the external normal, the direction n alpha, and I define a geodesic c of t to be this geodesic. So let c of t be the unit speed geodesic with c dot at 0 equals n alpha. C of 0 equals x, and c dot of it starts like that.
What is C1? Okay.
What?
So,
C, I don't care what it's here for. Just it's a geodesic that starts. It's
somewhere. Okay.
time 0 it starts here and it goes in this direction. And and look at okay, let's roll the picture. This is d alpha less than a, and this is x. This is n alpha, and the external normal, and we have here a c of t. And this will be beta times c of t. So it's orthogonal here. So okay. So so you see, because the projection here shrink distances, we have the fact that we have that the function t goes to d beta of c of t, which is the distance between c of t and beta c of t, is monotonically increasing. It's monotonically non-decreasing.
Doesn't it have to increase? Really
What?
increase? Doesn't it have to really increase?
Not necessarily. Okay, in most cases, yes, but a priori, yeah, I think it has to really.
Maybe it's
Thank you.
one, right?
Yeah, if no, okay.
I mean, if it's an
Okay.
Euclidean space.
No, it doesn't have
course.
to. It doesn't have to.
Okay.
And no, it doesn't have to. I can give you one. But you have this function. So let's call it. Let's actually denote it by f of t. And then differentiate it. So we look at dt at time 0 of f of t. What is that? This is the gradient of d beta times c dot of t. But by definition, it's a gradient of d beta times n alpha. So you see, so, and we know that this is non-negative.
I mean, c dot of 0, right?
Yeah, see that this is 1. So, and we know that this is non-negative, and furthermore, we know that this is proportional to n beta. proportional to n to the normal. Okay, so we disprove the theorem.
You don't need exactly and
This is the inner product between two vectors. If it's non-negative, it means that the angle between them is at least
yeah, no, but what do you mean
Is
it's
it-
proportional to m?
what? It's proportional. It's up to a scalar.
So the definition of m equals exactly
N beta was the normal vector, the unit vector in this direction.
the hat is like taking the unit.
Yeah. It's not a
I was trying to figure out what you meant by that.
what?
It's standard.
No, it's no, I just didn't realize it.
Yeah. Okay. Here in what I discussed here, v hat is v over.
Okay.
Maybe I don't know if it's standard. Okay. So this
Well,
proves
maybe it is.
this proves this theorem. Okay, let's go further. Discuss a bit more abelian groups. So here's another lemma. If name A is an abelian group, A is gamma 1 up to gamma n, an abelian group. Actually, I don't need it to be finitely generated. A is abelian. The group of isometries. Then consisting of semi-simple elements, and then S, which is the minimum of A, is the intersection over all A in A of the minimal set of A.
What do you mean A?
Or
It's.
I define it like
I
that.
thought- no,
It's-
this is intersection.
Now it's clear, instead of all points that every element in A attains the minimum of the displacement, is non-empty, and S decompose in the following W cross R L, and the action and A acts on S. So of course S is A invariant. S is A invariant, and any element, any gamma in A acts by ID translation. So it acts here trivially and here by translation. Okay, I think this is you prove it by induction on okay, if A was finitely generated, then you can prove it by induction on the number of generators. But if A is in general, you can prove it by induction of the dimension, because X is a manifold. A itself is S is a totally geodesic this is a totally geodesic submanifold. S is totally geodesic submanifold. And the way to prove it, let me do it hand waving. But this lemma is also in this book, Schroeder. But the way to prove it is just look at one element in A. We know that every semi-simple element acts like that. It has a minimal set, and the minimal set decomposes as a product of there is not like that, but for one element it will decompose like W prime cross R, and it will act like trivially here and by translation. So this the minimal set of a single semi-simple element. Okay, if gamma is elliptic, then it's just that. But if gamma is non-elliptic, then there is an axis. And if you look at all the axes of the element, they're all parallel, and the union of them is like that, and it acts trivially in translation. Any element, any semi-simple, any hyperbolic element acts like that. So take one hyperbolic. If there are no hyperbolic, if there is elliptic element in A, then look at its minimal set. If it's non-trivial, then it's a smaller dimension, and then you continue by induction. You conclude by induction. Because this group is commutative, then the minimal set of one element is invariant under all the rest. Therefore, you can apply induction. If there is no elliptic element, all elements are hyperbolic because we assume they are semi-simple. Take one of them. Its minimal set is of this form, and it's invariant under the other. So look how the other act on it, and then they will preserve this product, and maybe another element will have another axis, and you see. So if you have now gamma 2, this will be gamma 1. Gamma 2 will act here as some gamma 2 prime, some translation. And this gamma 2 prime is semi-simple. So gamma 2 prime acts as you can decompose this to W prime prime cross R, and the translation and the action of gamma 2 prime is fix this and translate this. But it's also the translation is something in this R2. Maybe it's not orthogonal to gamma 1. But okay, yeah, so you see that. So both gamma 1 and gamma 2 act by translation on this and fix this. And then you continue by induction of the dimension until you decompose everything. So the minimal set all the time shrinks. So wait. Sorry. So this set. Sorry, this set is So it acts by gamma 2 and translation, and the minimum of the minimal set for gamma 2 will be W.
Gamma 2 prime maybe?
Yeah, okay. It's the minimum set of gamma 2 prime will be W prime prime cross R. This will be inside W prime cross R, and you see that maybe it's smaller. Maybe this W prime prime is smaller than W, and no. If it's prime, it's like that. And okay, and gamma 2 prime acts here by so you confuse me with this. The minimal set of gamma 2 intersect the minimal set of gamma 1. Right? We saw that if isometry preserves some convex set invariant, then the displacement function, if it attains the minimum, then it also attains the minimum on this convex set. So the minimal set of gamma 1 is gamma 2 invariant. It means that the intersection is non-trivial. Okay. And now, each of them has a decomposition. W2 cross R and W1 cross R. Each of them decompose like that, and each of them preserve the decomposition of the other. So from this you deduce that the group gamma 1, gamma 2 acts on the intersection of both is some W, if you want, 1, 2 cross R 2, and okay, and they act here trivially as by intersection. So when you go further by
Can you explain the last part?
to explain it in different words. So
You can use the same one to say it again.
to say it again. So okay. So you have this, and now gamma 2 is semi-simple and it acts here. So minimal set of gamma 2 prime is inside W prime, and this set is of the form this set is of the form W prime prime, if you want, cross R, and it acts trivially here and here by translation. Okay, and you have this other R that comes from this, and so it acts trivial here and by translation on this R too. That's how gamma 2 act on a subset of So all the time you reduce the dimension of this the fixed set, you increase maybe by less the dimension of the translated space. So, and at the end you will left with something which is non-empty and decompose like that, and it actually is fixed.
L is like the dimension of the hyperbolic part. Okay?
Sorry?
L is like the dimension of the hyperbolic part.
L.
All the hyperbolic axes.
Yeah, L is the L is the dimension of I think okay. What you can deduce is the following. So here maybe this is what you want to say. So corollary. So if A acts freely, there are no elliptic element, then A is isomorphic to Z to the L, because it will act freely on some set of this form, which it acts trivially here and by translation here. Yes, it could, yeah. Maybe this W, basically, there is some ambiguity in this decomposition, because maybe W also has some Euclidean factors. Then you could add them here, but it actually is trivial on them. So then you would say that A is isomorphic to Z to the K, where K is at most L. So, but you can add it to this place where it acts trivial. Okay, this is basically the action of a abelian isometry group. It's very, very nice. Very easy to understand. Now, what happens if the group is does not consist of semi-simple elements? So then there is another lemma. Again, we assume that A is commutative. If A is a subgroup for the isometry of X, is abelian, and abelian and A is does not consist of semi-simple element, and A contains a parabolic element, then there is a fixed point, an A fixed point, zeta at infinity, the visual boundary, and A preserved the horosphere around this point. So last week we discussed a bit about Horo function, Guzman function, horosphere are the sublevel of this function. And basically, you think of them as the distance function from a point at infinity. All functions are a limit function of distance function from points where the point goes to infinity. You have to subtract things, so there will be a finite limit. So the limit will be well defined. Sometimes you consider them up to additive, so up to can have constant, and so we consider equivalent classes. And there was also a lemma that we mentioned that if you have a convex function, a convex smooth function whose gradient has norm 1 at any point, so the differential is norm 1, then which is equivalent of being one Lifshitz, and okay. It's gradient is norm 1 everywhere, then it is a Guzman function. So that was a lemma that we didn't prove. But anyhow, that's a Guzman function. And so I claim that there is such a point, and there is and the proof is, again, proof. Let gamma in A be parabolic. Let delta be the infimum of d gamma over all x, so the infinite value, so the infinite value, and this it could be 0 if it's strictly parabolic, but it could be positive. But the minimum is not attained. That's what means that it's a parabolic, but it doesn't have to be 0. And now consider A, which is bigger than delta, and for such A, look at fix some x0 in x, and look at the following function, fa of x. I define it to be the distance of x from the set d gamma less than a, and I want to normalize it, so I don't want, okay, I want to subtract the constant constant will be the distance of x0 from the same set. So what is happening here? We have the Hadamard space, and we have a parabolic element, so it does not obtain the minimal value, and we look at the this is a set where d gamma is less than a. And if we take smaller and smaller a, this set will become smaller and smaller. And if I have a point x, I look at the distance, fa will be the distance from x to this. So it will, if I don't normalize it by this constant, it will go to infinity. So I pick some x0, which is the center of this Hadamard space, and I subtract this. So then the value of this function here will always be at most, it will be 0 here. And here it will be at most the distance between x to x0. And this function is a gradient of norm 1 at any point outside this sublevel set. And the sublevel set somehow go to infinity, so in the limit it will have gradient 1 everywhere. So this function tends to a Hall function. So the limit when a goes down to delta of fa will be a Boozman function. We don't have a notation of a Boozman function around some point at infinity. And since all these functions are level sets of gamma, they are invariant under any isometry which commute with gamma. So also the limit function, the limit Hall function will be invariant under the full group A. So this fixed point, this point at infinity, and this Hall function will be. Okay. So this is one thing. This is important because why? Let me tell you the hint of before we go to the break. After the break, we discuss more general groups, which are not abelian anymore, but still important. But why this lemma, what we proved is important. So first, the fact that I told you that I told you two things. One thing is that the gradient of if alpha and beta commute, then the angle here is at least pi over 2. Right? This is one thing. Another thing I told you, that if you have a group of commuting isometries, then either there is some nice set on which it acts by translation, or there is a Hall function which is invariant, the Boozman function. If there is this nice set, and I'm not in this, I'm outside this nice set, then I can look at the direction that points away from this nice set, and the gradient of any isometry that preserves this set will be correlated with this direction. So the displacement will increase in this direction. I will prove all this. I will mention. I just tell you the motivation for what we did. This is in the case of the semi-simple case. This nice set which is invariant, and away from this set, I'm increasing the displacement function of all the isometry group that I consider. You have a question?
Yes. If you have an elliptic element.
Wait a minute. So yeah, okay. The elliptic are a bit more complicated, but still this is true. And if you have parabolic, then there is a fixed point at infinity, and the direction that points at any point in the direction that points away from this point at infinity, the distances, the displacement function of this commutative group will increase in that direction. So in any way, it allows us to to find this desired direction that increase the injectivity radius, and it tells us the angle of the corner at the boundary of the fix. So it's the two things that we would like to have, but so far only for commutative groups. So okay, we start with the distortion in group, distorted element. So definition, gamma in a finitely generated group, let gamma be a finitely generated group, and we consider the Cayley graph or the word metric, and this will be the word metric corresponding to this generating set S, and an element gamma in gamma is algebraically parabolic if its power is sublinear. The length with respect to the word metric of its power is sublinear. And a remark, which is obvious, if gamma acts by isometries, in a subgroup of isometries of Hadamard space, then every algebraically parabolic element, gamma has infimum of d gamma equals 0. Because if otherwise, we know that because we saw that if we call this, we didn't have a name for that, right? We should call it the norm of gamma, maybe. The norm of gamma. So we saw that the norm of gamma to the m is m times the norm of gamma. We had this, we proved that last time. So, okay, it's easy to see it for semi-simple element. If it's hyperbolic, then it has some translation, but it's a bit less easy to see it in general, but it's true. So in particular, it follows that the norm of gamma, the displacement norm of gamma is 0, which implies that gamma is either elliptic or parabolic. Or strictly parabolic. It is strictly parabolic.
What's the relationship between the norm and the word norm?
No relation. I don't say there is a relation. This is maybe it's not cool. It's it's related to, if you want, the spectral radius. We saw that this norm equals the limit of d gamma of x, d gamma to the n of x, and this is independent of x. We saw that last time, and so it's remind a bit properties of spectral radius, or right, if you want, but and it's true for matrices. It is a spectral radius in a sense. There's a relation between the eigenvalue and the displacement. Right?
I mean, Theorem, you need to say that. Okay, I see.
Something false here?
No, I just it's not. I mean, it sounds obvious because you write the norm and
No,
here.
yeah.
It's pretty obvious.
It
anyway.
relies on this, which is not completely obvious from last week. And
I mean, you don't need only the fact that gamma to the m, the norm of gamma to the m is m, the norm of gamma. You also need the fact that for every word you can do it.
no.
Because you want to take the, I mean, you think of gamma as a word in S, and then you bound the norm of each element in S.
Okay. Okay. So and if we speak about manifolds, so there are no elliptic, so it implies that algebraically parabolic is parabolic. And now there was this nice lemma. The lemma is nice, but I hate computation with commutator, so for me it's not so nice. So here is a lemma. If you have an important group of class 2, so suppose alpha and beta are isometries. Oh no, are elements. So suppose you have a group alpha, a group generated by alpha and beta, and the commutator commutes with alpha and beta. So in other words, that the alpha and beta generate an important group of class 2. Then you do some computation, and and you get then you do some computation, and you get that then alpha beta is algebraically parabolic, and the proof is the following. So alpha beta in the form you can see alpha beta alpha beta alpha beta alpha inverse beta inverse alpha beta it's alpha beta alpha beta beta alpha inverse alpha beta beta inverse. This is, for in my opinion, the most difficult things in mathematics. This computation of commutator alpha square beta alpha beta alpha inverse beta alpha inverse beta inverse, which is alpha square beta beta alpha inverse beta alpha inverse beta minus 2, which is alpha square beta square. Okay, I leave it to you to verify it. But this implies, if you by recursive step, that alpha beta to 4 to the n is like alpha to 2 to the n beta to 2 to the n. So the word norm of alpha beta to 4 to the n is at most 4 times 2 to the n. So you see it's what? Okay. Maybe I have some spelling mistakes here, but the corollary, or the real lemma here, is the following. Let's go to proposition. Position.
So you need some constant, right?
What?
You need some constant at the end, right?
No, the group is generated by alpha and beta.
Ah,
Now alpha and beta are in, but if you change the generating set, the properties of being algebraically parabolic doesn't change. That's a
but in
quasi-isometric.
a larger group it might not happen.
But it still be, if you have inside a group, you have such an element that this will be algebraically parabolic. Because you can express alpha and beta in terms of the generators, and there is some small exercise there. But
So if you enlarge the group, elements stay algebraically parabolic?
yes, sometimes something which was not algebraically parabolic can become algebraically parabolic in a larger group. But if you already algebraically parabolic, you will be also in a larger group. And the proposition is that let n be an important group of class K. So you know what I mean, right?
Okay, steps.
What? K steps. Then n to the k minus 1 consists, and here I say that k is bigger than 1. Then consists of algebraically parabolic.
Why do you need to be bigger than 1?
What?
Why do you need to be bigger than 1?
No, because if it's what? Otherwise, it's not true. If for a abelian group, it's not true that I'm going to use this lemma and the proof. What is this? You know what I mean by this, right? I take the first n to the 0 is n, n1 is the commutator, n2 is the commutator of the commutator with the group itself, and so on. And the proof is as follow. The proof is as follow. So every gamma in this n to the k minus 1 is of the form a1 b1 times a2 b2 al bl well it's a product. This is a product of commuting commuter. Okay, you can. That's every element in this group. You can express it that way, and each such element is algebraically parabolic by the previous lemma, and therefore, and since they are commute, it follows so the result follows from the
You mean center commutator?
yeah. What?
You mean center commutator?
What? This is a subgroup of the center. It's not the full center.
I know, but you said that it's product of commuting commutator. You mean
This
center?
this commute with that. This commute. All of them.
You want each one to commute with A1 and B. I mean, you want
No,
each
no.
one.
No, this commute with this commute with that, this commute, they all commute. I mean,
But the reason that each one is algebraically parabolic is because it's centered.
This is algebraic parabolic.
Why? Because it's centered.
All this, yeah, this is in the center, yes. Yeah, they commute with each other, and in this commute with A1 and B1. So this one is algebraic parabolic, this one is algebraic
And
parabolic.
why does it commute with A1 and B1? Because it's centered.
Because it's in the center, yeah.
That's
Okay. So what do we get? So the corollary is that if we have a corollary if gamma is a discrete group of isometry of Hadamard space, if not even discrete, and let's say discrete order 3, and gamma is let's say, suppose it's nilpotent and non-abelian, then there is a central parabolic element in gamma. So if gamma consists of semi-simple element, if gamma as before consists of semi-simple element, and by the way, this is in many cases this is the case. For instance, if the manifold, the quotient manifold is compact, maybe I should give it as an exercise. Then this is the case. Then gamma is commutative. You cannot have a parabolic element. Okay, let me give it as an exercise. If M is X mod gamma, a compact manifold, then gamma consists of hyperbolic elements. So any elements, there are no parabolic and no elliptic. So if you want, I will solve it, but not right now. So this is, so you see, there will be a dichotomy. Either there is a central element which is parabolic, or there is or it's an abelian group. And okay, but but it could be more involved. So here is another lemma. We want to understand this group better. So let n be an important group of isometries of the Mars space, and let H inside n be the set of all gamma in n, such that gamma is semi-simple. Okay, this is basically what confused me before. I want to say in this form. Then One, if H is non-trivial, then H contains a central element, non-trivial. Central. Then H intersect non-trivial isn't central. H intersect with center of N is non-trivial. 2, H is a group. Three, H is abelian, and min H S is non-empty and decompose as W cross R L and this decomposition is gamma invariant. So any element in gamma acts by isometry on W and my translation here, and H acts by ID translation. So let's call it a proposition. It's a bit more important than that. But you see, if you think about it, if you have an important group of isometries, then either it's abelian and everything is simpler, or if it's not abelian, then in the center you will have both parabolic and hyperbolic. And the group of all hyperbolic elements is commutative, and it's actually, if the action is free, it actually will be Z to the N, the hyperbolic element. Okay. Before we prove the proposition, let me formulate a lemma which I should have done in the previous hour. Lemma: if alpha and beta are commuting, alpha and beta are commuting semi-simple, then also alpha beta is semi-simple. And the proof is we saw that if we saw the beginning of the previous hour, maybe I did too much hand waving and not enough writing in the proof of this lemma, but we saw that if alpha and beta commute, then the group generated by alpha and beta, we saw that the minimum is of the form W cross R 2, and the action is, and they both act by ID translation. Right? That's what we saw. If you believe my hand waving. So you see, to compose to translation, you get a translation. So it's again same thing.
So they don't have the same axis.
Sorry?
I don't know they don't have the same.
They don't have to have the same axis. But
If they did, then would you get R and R2?
if they did, they may have the same axis. Yeah, they may have the same. Maybe I should give some examples. Okay. So you see that's the lemma, and now let's go back to this. So first, in the beginning I don't know that it's a group. Of course it's normal if it's a group, but I don't know if it's a group. But I claim that if it's not trivial, then there is something in the center. So why is that? Proof of the proposition. Proof of that. So first you say that, okay, let gamma in H be, it will be in H and inside n to the I, non-trivial, where I is maximum. So I take the most central element that I can inside H. And I claim that it must be on the center element. Okay? So if gamma is not in the center, there is a alpha in n such that gamma alpha is not trivial. But what do I have? Gamma alpha is not trivial and gamma commutes with gamma alpha. Right? How do you get this alpha? You look at gamma alpha. If it's and then you look at gamma alpha, and then if it commutes with gamma, you are happy. If it does not commute with gamma, then you do this.
What is gamma alpha?
What? You call
If
it
it commutes with gamma alpha, you are happy.
no. I want to get alpha, right? I take some alpha such that the commutator is non-trivial. If gamma commute with gamma alpha, I'm happy. Otherwise, I call this alpha and continue. And then after finding my step, it's nilpotent, then I will get it. So I have this property. But then, if you look at it, you see that gamma also commute with alpha gamma inverse alpha inverse, right? Because it commutes with gamma times this. But it also commutes with gamma, so it commutes with this. Gamma commutes with the commutator. But it commutes with itself, so I can delete this. So it commutes with that. But now I have two, and these are two semi-simple elements. Because gamma is assumed to be semi-simple, and this is the inverse of gamma, so it's semi-simple. And it's, to be semi-simple is conjugation invariant. So you get that gamma alpha, gamma inverse, alpha inverse, which is the commutator, is semi-simple, a contradiction. So it's a contradiction to the fact that gamma was not in the center. Okay, so we prove one. We prove that if H is non-trivial, then it has a central element. Now you can prove that H is a group. Why? Now you can prove everything, that it's a group and it's decomposed, all the rest now follow after you know that there is central element, because because you look at them, let gamma be an element in H and the center of N, and let minimum gamma be S And it's decomposed as W cross R. Forget this decomposition. So S has smaller dimension, and this S is invariant under H. Any element in H preserve S. So what am I saying? So any element in S okay, you can prove by induction on the dimension of the space that you act with. You can prove everything by the induction on the dimension, and you have this gamma. Suppose we allow such thing. This is actually it's a totally geodetic submanifold. It could be and the dimension of this is smaller, and so I can argue by induction on the dimension. And you can prove by induction on the dimension will follow that H is a group and everything. So it's a group, then it acts preserving decomposition. W prime cross RK, trivial translation, so it's an abelian. Now, after you know that there is a central element, you look at its minimal set and you continue by induction. When you prove such a result, you first need to consider if maybe you first need to prove it for Rn. Okay, this was again a bit hand waving, but I will discuss with you after the details. Anyhow, this lemma also appear in Barlow-Schroeder, so the consequence is that inside an important group, the semi-simple element form an abelian group, and they intersect the center. And if everything is semi-simple, then the group is abelian. And otherwise, there is a parabolic element in the center. And more than that, if it's semi-simple, we know how they act. They have some subset that they act trivially here and the translation. And okay, so this is all the geometric information that we need in order to prove the following, we call it a theorem. In fact, here they prove something more general, but let me formulate it in the not full generality that they prove, but in a nicer way, I think. And the theorem is the following. So let n be an important group of isometries, and let x be a point in x, then there is some direction in the tangent space such that for any gamma in n, such that x is not in the minimal set of gammas. In particular, if gamma is parabolic, the minimal set is empty. If gamma is hyperbolic, you don't want x to be on the axis of it. And if gamma is elliptic, you don't want x to be a fixed point. But of that element. If you are, then it's okay. You just forget about this element. For any element gamma which is not does not contain x in the minimal set, you have that the gradient of d gamma times the n is non-negative, is positive. It's positive. So you see, if you will go in this direction, you will increase the injectivity radius with respect to every gamma which does not attain the minimum there. And if gamma attains the minimum, then at least you don't make it worse, because you're already in the minimum. So there is some preferred direction in terms of injectivity radius. Okay, we will prove it next time. Maybe I owe you a bit more explanation about this decomposition, right? Maybe I think you are not happy by my hand waving saying do induction, right? So I will say a few words about it in the beginning of next time. Okay, let's see you next week.